Okay, hello and good evening to yet another, probably my 32nd or 33rd live stream this year. We're going to be doing GCSE for the first half an hour up until, I always forget which side it's on, up until we get to about 8 o'clock. And then from 8 o'clock onwards, we're going to be doing some A-level stuff, hopefully preparing you, if I can, for paper 3 coming later. There is a poll up in the live chat all about your GCSE chemistry paper 1 that a lot of you will have done earlier. Hopefully the paper was okay. So far though, the first vote basically says not so nice. So hopefully it'll get better as it goes on. However, I'm sure that as time goes on and you do your physics, everything is going to become so much better. Because a lot of people have actually said that physics is kind of easier because a lot of it's just maths, and if you've got the equation sheet, it's just putting numbers in. So hopefully it's all going to be good. Now, the questions tonight are from one of my practice papers. I'm sure I keep going on about it quite a lot. But you can buy these in my online shop. And tonight we're going to be looking at some questions. We're going to probably be looking at questions 1 and 2. Is this going to be for WJEC Unit 4 Physics, possibly? So the topics, so the first bit is GCSE. We're going to be looking at some forces, and then we're going to be looking at refraction. So if those topics come up in WJEC Unit 4, no, I see your next comment is A-level. So the first bit is going to be GCSE. The second part is going to be more kind of generic skills about how to deal with the practical assessments and those experimental things and some log stuff. Okay, so Anissa, hello. Sala, hello. Hope you're all good. Right, first of all, the first question says tick 2 boxes to select 2 equivalent units of work done. So when we're talking about work done, this is going to be the energy that's transferred maybe to an object. So maybe you do work on something and energy is transferred. And of course, we always measure energy in joules. Okay, so the first bit is straightforward. Now, I suppose if you know that that one is joules, we know that newtons is a different one. So Newton is what we measure force in. So that's nothing to do with the energy. And it can't be joules per kilogram. So it definitely can't be that. The next thing then is what's an equivalent unit. So what is the same as 1 joule? Well, you might remember, and again, if you're not sure, then you can of course look in your data sheet and you can still check on that because that will give you clues. The work done is equal to the force moved by the distance in the direction that the force is acting. Okay, so sometimes it might be F times D or F times X, but basically if you know the force applied and the distance through which that force is applied in the same direction, that will tell you the work done. And we measure, I'm just going to go to a different, I'm going to go to green for units. We measure our force in newtons, and we're going to multiply that by the distance in meters. And that means a joule, the unit, is the same as a newton meter. So a force of 1 newton acting over a distance of 1 meter will transfer 1 joule of energy. And that's why Newton meters is the second answer. So basically, both of these things here are equivalent units. Okay, Evil, yo boys and girls as well. There's all sorts of people in the chat. You failed further maths today. Don't worry about it. Put it behind you. Now, Austin, we are doing GCSE for the next half an hour. Okay, somebody, so we've got Chidambaram saying, as long as you know your specification, all physics questions are good. Yeah, and basically, yeah, the fundamental understanding is the same. I agree with that because, you know, whatever A-level you're doing, it's going to prepare you if you want to go on and do physics at university or some kind of STEM thing, and it's the basic understanding is going to be identical. And this thing here, you know, if you understand the basic physics, it doesn't matter which exam board you're doing. Anissa, manifesting for a 9. I'm sure you'll get it. Also, you need to do some work as well, but I think if you're aiming for that 9, you can definitely get there. What do I think the hardest topic will be on Friday? Daniel, I reckon the hardest topic is often the one to do with electromagnetism. So about, you know, the current in a solenoid. So that's a coil that can carry or allows a current to go through it, and how that's linked to magnetic fields, and maybe then like Fleming's left-hand rule. I think that's often kind of one of the most difficult parts that most students find difficult. Okay. Okay, so explain why no work is done in each of the following scenarios. So again, we've put up here, I'm just going to write it out again massively. Work done is equal to the force times the distance, and this distance here is the distance moved in the direction of the force. So we've got an object moving a distance of 1 metre without any forces exerted on it. So potentially, you know, this is like our ideal situation of maybe something in space that's a long way away from any other planets. There's no gravitational forces acting on it, so this is kind of this imaginary perfect scenario, or the distance is so big that any gravitational forces of attraction are negligible, and it's just moving along. Now, of course, the work done is force times distance moved in the direction of the force, but here, the size of the force is 0, and therefore 0 times the distance is going to be equal to 0. So the work done is going to be 0 joules. So no work is being done on that object at that time. A piano of mass 480 kilograms remains at rest in the house. Now here, because it's at rest, that means the distance travelled is going to be 0. And of course, again, the work done is equal to the force times the distance, which is equal to whatever force might be acting on it, times the distance of 0, which is equal to 0. So that one there, again, now rather than having the force being 0, the distance travelled is 0. So you only transfer energy to something, in this case when it's moving. Now the next one, we have a planet orbiting the sun in a perfectly circular orbit. So for that, I'm just going to draw my diagram. So here is my perfectly circular orbit. Here we have the planet, and here we have the sun in the middle. Now here, a force is being applied. There's going to be a force of attraction of the sun pulling in on the planet. Okay. However, at any particular point, the planet is going to be moving maybe this way or that way, depending if you're looking up or down on it. And here the force is going to be at 90 degrees to the direction that it's travelling in. And that means the force on the planet is perpendicular to the direction of the planet. So the distance moved in the direction of the force is 0. So again, we said that the work done is equal to the force times the distance, and I'm putting an asterisk there to show that this is the distance moved in the direction of the force. So it's not moving in the direction of the force. In fact, it's moving at 90 degrees, and there's no component of that force acting in the direction. And that means it stays at the same speed and continues in a circular orbit. Okay, let's have a look at what people are asking about. A Fox plays, do I reckon I could do magnetism and microphones, and do I have predictions for Edexcel physics? It's very hard to make predictions, I feel. I've never been able to do it properly. So I reckon the paper will be fine. That's my first prediction. If I'm not doing microphones tonight, which I don't think I am, if you want to find anything else, then you can go to GCSEphysicsonline.com. I've got a website, there's like over 500 videos where I go into lots of detail about microphones, about electromagnetism, about all of that good stuff. So if there's anything you're not sure about and want to teach yourself, you can also find the videos organised for Edexcel on that page. Okay, so the first page, questions okay. Right, let's have a look. A ball is thrown vertically upwards by a person standing on the Earth's surface. During its time in the air, energy is transferred between different stores. So, state the name of the force on the ball due to the Earth's gravity. So, again, I think something like this, it's always nice to maybe draw a diagram. So, here's the Earth. Here we've got a person, and they basically throw a ball, which I'm going to do in red, and they throw it, not to scale, of course, they throw it into the air. So, maybe it's going up at some point, maybe later on it's travelling down. However, when it's in the air, there are going to be some forces acting in it. There will be a force downwards, and that is the weight of the object. Now, the weight force down is due to the Earth attracting the ball, and of course the ball, if we were to extend this diagram to be the whole Earth, there'd also be a force of that ball pulling up on the Earth. And this force here, I'm going to call it W dash. These are a pair of forces. So this is an example of Newton's third law. So the force of the ball on the Earth is the same as the force of the Earth on the ball. So here, the force on the ball due to the Earth's gravity is weight. Okay. Okay, so yeah. Okay, Fox says you're a little worried about paper 2 as you found paper 1 to be really easy. That's a good position to be in, finding it straightforward and kind of flying through the paper. A Fox plays, yeah, I reckon that just means that you've prepared really well. You've been doing some, I guess, quite difficult questions, and you've been, pretty well prepared by your teachers, I'm sure. So if you found paper 1 easy, basically paper 1 doesn't really reflect onto paper 2 normally. So it's like, I've seen so many times where paper 1 is hard, paper 2 is easy, paper 1's easy, paper 2's easy, paper 1 is easy, paper 2 is impossible, as we saw like earlier this week with A-level. But paper 3 is a completely different thing. So yeah. Okay, is my 4th daily workout book out yet, Joe Smith? Yes, it is. It's been out for a while. The 5th one is still a bit delayed because I've been doing other things. So book 4, if you're year 12, this is like not for the GCSE lot. If you're in year 12, then you can buy this, and there are questions every day from July. And I think this one's also got the index in the front, so you can see there's questions that basically take you from year 12 knowledge into year 13 stuff. And then there's loads of stuff about circular motion, simple harmonic motion, particles, gases, all that good stuff. So it goes up until the end of October. And of course, the GCSE crowd, some of you are watching at the moment. If you are doing A-level physics, buy book 1. This is one of 3 books. So I've got book 1, 2 and 3, which are for year 12. Book 4, 5 and 6 are for year 13. But I'm still working on these 2, so I want them to be the best thing ever. And basically there are questions for every single day. So on the 1st of July you just do this question. On the 2nd you do those questions. On the 3rd you do these questions. On the 4th you do these. And it builds up over time. And that means by the time you're getting into September, that means you're kind of ready for the kind of new challenges of A-level. There's like resolving forces, there's loads of good bits and pieces, introduces new knowledge, and this is ideal for the start of year 12. What's the difference, YT, Shebzi? Basically, it's just the content. So books 1 is like for like GCSE into A-level. Books 2 and 3 develop more the kind of stuff you do over year 12, sorry. Book 3 is basically a revision for everything in year 12, including lots of practical stuff. Book 4 then takes you on to like some of the year 13 topics. Yeah, right. The next question then, describe the energy transfers occurring while the ball is travelling upwards. So we're just going to we're going to ignore the fact the ball might be going down, okay? And we're going to think about the ball as it moves from the surface of the Earth, maybe in this position, as it goes higher and higher until it gets to the very top. Now initially when you throw it, it's going to be moving with the greatest value of velocity, and as time goes on, the velocity gets smaller until at the very top it gets to 0. So we can say that the kinetic energy store of the ball is transferred mechanically to the gravitational potential store, and also there's going to be some energy transferred to the thermal store, and this is because there's going to be a force acting on the ball due to air resistance or drag during its motion. So provided this is happening in air, there will be a drag force, which means that some of that kinetic energy is transferred to the thermal store of the surroundings, maybe to the ball as well. And it's a mechanical transfer because what we have is there's a force acting over a certain distance. So there's going to be a drag force acting on this, and there's going to be the weight acting down. It's going over a certain distance, and when you have a force applied over a distance, we have mechanical working, which in this case is increasing the gravitational potential store of that ball. Okay, there we go. Hopefully that's all good. Right, the next one. This question here is about refraction, which is something which is covered a bit more in depth, especially for those students, probably like a lot of you, doing triple science or kind of separate science. By the way, in the chat at the moment, especially people doing GCSE, people like Naxan and everybody else, let me know if you are doing triple science, so you're doing a separate physics, separate chemistry and separate biology, or if you're doing combined or trilogy. So yeah, it'd be amazing to find out if you're combined or you're triple. Okay, all of you are welcome, and a lot of the stuff I'm doing is going to be suitable for everybody. So the first bit is about refraction. Okay, so refraction occurs in light, and that's where it's quite nice to see it in the classroom if you use some laser light or even just a ray box, and you can see the way that the light bends as it goes from one medium or one material into another. But it also happens on other types of electromagnetic radiation, and also things like sound waves can refract, and also lots of waves have similar properties, so they can diffract, refract, some kinds of waves can be polarized and so on. Okay, so let's see what people are doing. Separate, triple, 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 separate. Okay, Hal, you're just doing physics and chemistry. You don't even have to do biology. That would be the dream for many people. I did like biology, but I preferred chemistry and physics. Triple for Temedola. Sala is doing triple science. And yeah, this kind of question, I think, might be more of a triple question, where there's a bit more detail about refraction. So, explain what is meant by refraction and why it's different. So we're comparing two things to reflection. So refraction is a change in direction of a wave as it passes from one medium into another, whereas reflection occurs at a boundary, but the wave remains in the same medium. So in the simplest diagram possible, if you've got refraction, and maybe you've got medium 1 and medium 2, if you have refraction, the light will either speed up or slow down as it goes from one medium into another. Of course, if you're going to do a ray diagram, do them in pencil. Make sure that if you need to do angles, you have your protractor ready. That's my biggest tip, is that loads of people forget their protractors. And you're going from one medium into another. So we've got straight lines drawn with a ruler with arrows on them. Whereas if you had reflection, what you'd have is maybe medium 1 and there might be medium 2, like a piece of glass or something. And as that ray of light or the wave hits this, it will reflect potentially like that. So what we have there is a lovely specular reflection. Okay, state two properties of light that have different values when it is travelling inside the glass rather than in air. So the two things that change are the wave speed, so how fast it's travelling, and the wavelength. So if we think about the diagram up here that shows wavefronts moving in, we can see that over here, if we were to measure the wavelength, so that's the distance between wave peaks, it's quite big, whereas as it goes into glass, which is optically more dense, so it slows down how fast that light is travelling, then we can see here that the wavelength gets much smaller. But if you were to stand here and count the number of waves going past every second, or you stood over here, if you could be that small, and counted the number of waves going past each second, the same number of waves would go past. And that's because the frequency stays the same. Now we know that there's a wave speed equation that says v is equal to f lambda. And effectively, because the frequency, the number of waves passing a point each second, stays the same, that means the wave speed is going to be proportional to the wavelength. And as the wavelength decreases as it goes into this medium, that means that the wave speed must also decrease. Okay, can you tell if it speeds up or slows down by the bend? I'm afraid I can't pronounce your name. But yes, so basically, the analogy that I've used, I don't actually have any toy cars here, but effectively, if you imagine, I think one example you could do like a row of like marching soldiers or something, but basically if something is coming in this direction, one bit, let's imagine their front foot, hits the other medium before the other, so it slows down first. And as they slow down, they bend towards the normal. Now the normal line, let me just draw that a bit bigger. Okay, so here is the medium. Okay, and maybe a wave comes in and it does this. Okay, now you should of course be doing this with your protractor. Now the normal line is drawn at 90 degrees to that surface. This is the angle of incidence and this is the angle of refraction. And if the angle of incidence is bigger than the angle of refraction, that's because something slows down. But if it's maybe going the other direction, so here we've got a ray of light going from maybe something where it's going fast to slow, it kind of bends towards the normal. Whereas if it was maybe going the other way, so let's maybe think about a ray of light coming in this direction, and then it maybe comes out like this. Again, we can draw in that normal line like this, but now the angle of incidence is relative to this boundary, this angle, and the angle of refraction is that one. So here, the angle of incidence is smaller than the angle of refraction, and therefore it speeds up. So potentially that could be light going into glass, and that's light coming out of glass. Okay. So in light, a more dense medium. Okay, and this is an important thing that's actually there. So basically, if you have light, and it maybe goes from air into glass, basically the glass is more dense, or it's denser, and therefore the light slows down. Now that's what happens with light. If, however, you have a sound wave is a mechanical wave. Okay, so let's imagine you had sound travelling through the air, and then that sound wave went through glass. Because this is more dense, that means if we think about the particles, they're going to be spread apart in air, and they're going to be really close in glass. And actually, because it's a mechanical wave, which is passed on by the vibrations of these particles, the sound wave actually speeds up, because it's quicker for the vibrations to be passed on from one to the other. So you can have air to glass, light would slow down, but sound would speed up. And we found with sound or ultrasound and things like that, they actually travel faster in liquids and solids than they do in the air. Okay, yeah, hopefully, if that comes up, I really hope that comes up, because I think this is a really nice bit of physics. And also, all of you watching this at the moment, you kind of get a bit of a boost if you've just seen this just now. Okay, right. So the next question. This question is, I reckon, a grade 9 question, because it goes beyond the kind of things which are normally taught in A-level. Okay, sorry, it goes into stuff that's not taught in A-level. These aren't facts you need to know about for GCSE, but it's more about looking at some data and analysing it. So this shows how the speed of light in glass depends on the wavelength the light has in air when it approaches the glass. So we're going to look at the speed in glass, and we're going to see how that relates to the wavelength in air. And basically, what we find is that when you've got light that has a longer wavelength, it has a faster speed. Okay, now you should remember that if we think about the visible spectrum and how that kind of relates to the wavelength, the longest wavelength is going to be up here, which is going to be red, and then the shortest wavelength over here is going to be the violet. So that's next to infrared, long wavelength, ultraviolet is short wavelength. Okay, so describe the relationship between the speed in glass and the wavelength in air. So we can say that as the wavelength in air increases, the speed in glass increases, but at a decreasing rate. So we can see that it's a 2-mark question. We can't just say as that increases, because that could be a straight line, or it could be a line that does this. But we can say that that decrease, the rate of increase slows down. Okay. Figure 3 shows the refraction of white light through a triangular glass prism. So there's not really much colour here, but basically what we can see is that red light is up here. I'm going to do a dot over here to show that's our red light. We have our violet light over here, and of course then we have all the different colours between this. Okay, I don't quite have all the colours. Oh, actually, completely coincidentally, got some Lego. I need to order some more Lego, so I've just been trying to work out what colours I need. We basically have this full spectrum of lights. You have white light shining in, and then we have red all the way through to violet. Okay, so the next question says, explain using figures 2 and 3. So we're going to use this data and that diagram. We're going to explain why the white light is split into different colours, which is an effect called dispersion by the prism, with violet light refracted more than red light. So this question is a difficult one to answer, but it's not about any existing knowledge. It's about you've been given some data, you've been shown a bit of physics, and can you explain this in terms of that? So what we can do from this graph here is basically look at the speed in glass, okay? So we can see that red light in glass is travelling fast, and the violet light is travelling slower. Okay, now over here the white light is travelling through the air and it's going to be going very fast. So what we find is the red light goes from very fast down to fast, but the violet light goes from very fast and it goes down more and it decreases to something which is slower. So what we can see here is that the change in velocity of the red light is small, but the change in velocity of the violet light is big. And of course, refraction is related to how much something slows down. So if something slows down more, there's going to be a greater amount of refraction than if something only changes its speed very slightly. Oh yeah, speed. Austin says, speed of light being called very fast is the understatement of the century. Okay, yeah, so it's very fast, and in the glass, that's fast and that's slower. But I mean, even slow light, we're talking about, 204,000 meters per second. But that's only really about, 67, 68% of the speed of light. So yeah, so that one there is where we are. So what I said here is that white light is made from all the different colours of light travelling at the same speed in air. So we've just stated an obvious thing. Okay, this is so obvious that we know white light is made up of red, green, blue, all the different colours of the rainbow. And the different colours all have a different wavelength, and that means they must all travel at different speed in the glass prism. So again, this is stating something, saying that basically all of the light travels at less than the speed of light in a vacuum or in air. This means that violet light with the shortest wavelength changes speed the most as it enters the glass, so it bends the most. And what we find is you have a greater amount of refraction, a greater bend or change in the angle of the light, which has the greatest change in speed. And that's why the violet is kind of split apart from the red, and we see a beautiful rainbow shining out of the other side of that prism. Sala says, what pens do I use? These ones here, about 10 years ago, I just found these. I tried loads of ones. These are V-Sign Pilot pens. They are brilliant, and they're especially brilliant that they work really well writing on A3 paper on this, and I think that I think it comes out pretty well, doesn't it? Okay, so that is basically the end of GCSE, pretty much almost exactly at 8 o'clock. So let me just get ready for the next part of the stream. Joe Smith says that seeing the year 13s get demoralised about AQA physics doesn't give you confidence for next year. Joe, do not worry about it. I know that with the way that AQA messed up a little bit last year, they definitely messed up again this year. There's a lot of teachers trying to do something about it. So there's going to be two scenarios. Either your school switch exam board, which can be done midway through the course because all the physics in year 12 is pretty much the same anyway. So your school might change exam board, or AQA realise that loads of schools are about to change and they definitely and drastically improve what they're doing. So don't worry about it. Ultimately, the people who've got good exam skills, the people who've done lots of physics will prevail. Okay, so it's just a case of, it is hard for everybody, but the people who've, I don't know, I'm just trying to be positive here. I think that people found paper 2 difficult, but the grade boundaries will be adjusted accordingly, which at least is one thing. Okay, thank you everybody. Temidola, Afox, Anissa, Sala, thank you everybody here for that first part of the stream. It's been great to have you. I shall be here again tomorrow, and also, is it Tuesday today? I'll be here Wednesday, I'll be here Thursday. I might do a last minute panic session Friday morning. We'll see how it goes. Okay, so, right, should we do some A-level stuff? Oh yeah, by the way, Sala, thank you so much for reminding me. Like the stream, everybody. You can press the heart thing. Basically, I'm about 20 seconds. You're hearing me now how I was speaking 20 seconds ago. There's like a little time delay. So yeah, it'd be great to have lots of kind of love in the stream there. If you're watching this afterwards, please do like the stream. And we're going to get started with some A-level stuff. I won't be doing A-level Sunday for paper 3 because I'm in Scotland this weekend. So I'm just nipping up to Scotland for a day. so I probably won't be back in time on Sunday night. I've forgotten now, is paper 3 on Monday, is it in the morning or the afternoon? Do let me know. So paper 3, is it Monday morning or is it Monday afternoon? It's morning, it's morning. Okay, so that means I probably won't be doing an early morning stream of that paper. So basically Friday is it, and basically then you're going to be fine. Right, tonight we're going to do some stuff. Again, I know that everybody doing paper 3 is doing slightly different things, different optional topics and so on, but we're going to be looking, again, this is one of my practice papers, this is the beta paper. If you want to download your own copy to kind of work through in your own time, you can find this in my shop. So, we've got a question about a pendulum, straightforward stuff. So the question has a part about how to take accurate measurements, for recording the time. We've then got an equation that you should be familiar with or you will have seen beforehand, and we're going to relate this equation to the real experimental setup. Then there's something to do with G, there's lots of information here, and then it goes on to looking at a different experiment, looking at damping on something undergoing simple harmonic motion. So again, this might be something you might have done at school, or it might be something which is completely new to you, but it doesn't matter, because a lot of the stuff you will get will give you new stuff that you're maybe not familiar with. Okay, so there's quite a lot to this question, including natural logs. Brilliant stuff. So this is just some exam skills that we're just going to sort of talk through, maybe look at some exam technique. So you've got a sixth form student looking at SHM. They've got a golf ball attached to a thin string, and they're going to investigate how the time period of the pendulum depends on the length of the pendulum. They fasten a string between two wooden blocks, which is great, and that means you can basically clamp this up and then you just undo the clamp a little bit. You can pull the string through, and that's a nice easy way to adjust the length. They take it to the starting position as shown in figure 3. How would they take an accurate measurement of the time period of their pendulum? So this question is, again, just absolutely basic stuff. I say basic. Basically, what you need to do firstly is think about the time for 10 oscillations. And basically, you then divide that by 10, and that's going to give you the time period for one oscillation. So basically, n is going to be sort of somewhere between 10 to 20. Okay, so you want at least 10 oscillations. Okay, count 10 seconds. Yeah, so 10 oscillations. The second thing is we need to use a marker. So we need to use a fiduciary marker, can be said. And basically, you'd put this at the bottom down here. Okay, that's just a little pointer, and this is our fiduciary marker. And basically, you start and stop the timer as it goes past this, where it's in its equilibrium position. It's moving at the fastest. That means it spends the least time in here. So if it's spending the least time there, you're going to have less uncertainty about when you start and stop the timer. Okay. The questions this year will tell us which practical they're in reference to. Right. Yes, that's right, Ben. So a question like this would say, this question is related to simple harmonic motion. However, you know that. It's a question about a pendulum. A lot of the time, it's almost like, it's kind of like obvious, you know. If it's an experiment about measuring G, you realise that from just reading the question. So they do tell you, Ben, this year which of the required practicals it's related to, but I reckon most students already know that it's a question about simple harmonic motion, and they can just remember how that relates to stuff they've already done. So fiduciary marker, and that's where you basically start and stop the timer. Okay, by just saying a mark on the board, will that get mark? A mark on the board? No, I think you need to say that you've got a fiduciary marker at the equilibrium position. Okay, the student is planning to use the equation T equals 2 pi root L over G in their analysis. Explain why using this procedure above is unlikely to give them results which agree with this equation. So, why is it that will not tell us the time period of this. Well, basically, if we're looking at this, what we have, as Meme Lord 69 says, the equation's only valid for small angles to the vertical. So here, if we think about the size of this angle, that's going to be like 45 degrees or something. That's actually, yeah, that's kind of like 55 degrees. So here theta is about 55 degrees. And this equation only works for small angles. And that's when we can approximate sine theta or tan theta to be theta. So we basically say that theta is too large. And then you can say the equation only valid for small angles. And I'm sure you've done this at school yourself. You've set up a pendulum, swinging wildly, smacking into the side of the bench. You need to have a very small angle of theta in order for this equation to be correct. Excellent stuff, Meme Lord, and everybody else who said that in the chat. Okay, the next question says, the student improves the method, records data for the time period t over a range of lengths of L. Use the equation given to explain how they could plot their data graphically to deduce a value for g, the acceleration of freefall. So we know that t is equal to 2 pi root L over g. Okay, and of course, actually, Austin, good point is also a valid thing that you could have said. This equation is only valid if there's no air resistance. So this is assuming it's a vacuum, and also, I suppose, it is in air, but there is a practical I've seen, I think I've done a question about it, where you have something oscillating with the end of something in some water, and basically that means you get quite a big damping factor. So again, that equation here assumes there's no air resistance. Am I going to go through the option topics? I'm afraid not, and I do have videos over at A-Level Physics Online where I go through those individually for the different parts of it, but I'm not going to go over it because I know that if I did an optional topic, that would mean that 75% of the people would find it wasn't useful for them this evening. Maybe next year for the current year 12s I might do some, but I haven't done some optional topic preparation, so I'm not going to go through the optional topics. They're going to be fine. This is what most people struggle with. So this is the equation. We're going to square both sides to say that t squared is equal to 4 pi squared L over g. Now, of course, we're going to look at values of t and we're going to look at values of L. So that means you can plot a graph of t squared against L. So it doesn't really matter which way round you have the axes. Let's say this is, for example, you could say that this side here is t squared, that's L. And if you plot this data, we can see that t squared is equal to 4 pi squared over g times L. Okay, now that means, if we think about how this relates, of course, to y equals mx plus c. On the y-axis, we might put t squared. On the x-axis, we put L. And that means 4 pi squared over g is equal to our gradient. And our intercept is going to be equal to 0. So that means you should get a straight line that does this. And of course, if you now work out the gradient is going to be equal to t squared over L. And t squared over L is equal to 4 pi squared over g. So if you want to work out the value of g, the value of g is going to be equal to 4 pi squared over the value for your gradient. And this means that you can take a range of data and then you can use that to work out what the acceleration due to gravity should be. Okay, yes, James says that is t against root L with 2 pi over root g gradient absolutely okay? Yes, it is. You could do this graph where you could do a graph of t against root L, and again, you would get a straight line. You could also do it where you've got root L against t, and you'd have a straight line, or you could have L against t squared, and you'd have a straight line. All of these are completely valid ways of doing it, and there's not just one correct answer. So all we're trying to look at is looking at this equation here, and we can see that we've got t is proportional to root L, so t squared is proportional to L, and that constant of proportionality is going to be related to the gradient, which then allows us to work out the value for the gravitational field strength. So James, great point. Okay, the student makes an error in measuring the length. They measure from the bottom edge of the wooden blocks to the top of the golf ball. So what they've done is been a normal kind of A-level student, and they've measured the length from here to here. So they've measured the length of the string. But of course, the length that we should be measuring, the correct one in green because it's correct, goes up to the bottom of the string and it goes up to the centre of mass. So again, the length is from the pivot to the centre of mass of that oscillating object. So, we've got information here. They use that graphical method to deduce the value of g, plotting time period squared on the y-axis against length on the x-axis. So basically, they've plotted their incorrect data like this. They've got t squared against L. Now, provided the time period of the string and measurement, show with suitable calculations the numerical effect their error will have on the gradient and intercept of the line that they plot. So, let's say that, okay, so the way that we could say this is they've measured the incorrect, I'm just going to draw a diagram to make this clear. Okay. Is this just plugging in values? No, it's not, Austin. We've actually got to do some kind of more interesting maths, okay? So let's imagine this is the pendulum and the thing at the end. Okay? Now, we can say that the length that we should be measuring, L, is this L over here. But what they've done is they've measured a value of little l, but we also have the radius of the ball at the end, r, as well. Okay, let's call it little r. Now, the length is actually L plus r. So the true length of that pendulum is the length of the string plus the radius of that golf ball. Okay, now we know from the graph up here that t squared is equal to 4 pi squared times L over G. But L is equal to this. So that's equal to 4 pi squared L over G plus 4 pi squared over G times the radius of that ball. Okay, now if we think about what's plotted on the graph over here, we've actually plotted on the x-axis. I'm going to draw this again. So we've basically got a graph where on the y-axis they've plotted t squared. On the x-axis they've actually plotted little l. Now if we think about how that relates to this equation over here, we know that t squared is equal to, I'm just going to try and do it in some different colours, 4 pi squared over g times L plus 4 pi squared r over g. Okay, now on that graph, basically on the y-axis we've got t squared, and that's equal to the gradient times what's on the x-axis plus the y-intercept. Okay, so basically what we've done here is we've got this on the y-axis, on the x-axis we've got little l, and now we have a plus c. So what we'd actually get would be a graph that actually looks like this. So there would be a certain value on the y-intercept when it should be at 0. Okay, so what this means is that the gradient is unaffected by this. All we've done is we've taken the graph that we should have got over here and the gradient has been shifted up. Now, if the gradient's been shifted up, what happens? With suitable calculations, the numerical effect that error will have on the gradient. So the gradient m is equal to 4 pi squared over g, and therefore no effect on the gradient. The other thing though is that there will be a value for the y-intercept which is equal to 4 pi squared r over g, and we can calculate that as 4 pi squared times the radius. So we've got the standard diameter here, so that's going to be 2.135 times 10 to the minus 2 divided by, say, 9.81. And we can then kind of work out the value on the y-intercept. So yeah, so the gradient is the same even if you measure the wrong length. It's a bit weird, but that's kind of the way it goes. So we've got 4 times pi squared times 0.02135 divided by 9.81. Sorry, 4 times pi squared times 0.02135, giving a value of C equal to 0.086. Okay, so we know that the value of C is 0.0086, and the units for that, because that's seconds squared, would be seconds squared. Okay, so that's the units. Okay, yeah. So it gave the diameter. So what I've done here is, yeah, so in the question, and this is why it's difficult, because there's so much information which is kind of hidden in different places. So we've got the diameter up here, which means we can work out the radius, which is related to this. And basically what we find is that in this case, the value of g doesn't change. All it does, and we can sort of show that because we know that the length, the actual length, was equal to the measured length plus the radius. We kind of put that back into the normal equation, which gives this. We relate that to y equals mx plus c, which happens all the time, and that then allows us to show mathematically that the gradient isn't affected, but there is now a y-intercept, and we can actually, with a suitable calculation, quantify that. Okay, how many marks would that be? I reckon that would be 3 marks in my paper, probably more like 4 or 5 in the real exam, but I think they guide you through it and they do it step by step. But yeah, I gave you 3 marks for that. Okay, the next question. This is again what they'll do. They'll kind of maybe introduce something that you're familiar with. So everybody's done pendulums, everybody's done a spring mass system, but not everybody's gone and got a ball which is rolling from side to side. So this one here, it's a new experiment. Again, it might say this question is related to simple harmonic motion, to give you a bit of a clue, but just have a quick read of that. So we've got a big, long track, which is 1.1 meters. Metal ball that's just going to go from one side to the other. And they aim to measure how the amplitude change from the central position to the center of the ball changes with the number of oscillations. So how A is related to the number of oscillations. How could you make accurate measurements to carry out that investigation? So the first one is a bit like, if you were given this equipment, what would you do to get accurate measurements? So basically what you could do is, yeah, you could basically, first of all, you put a ruler down, and your ruler might go from the center of the track and it goes out this way. So the first thing is you need something to measure the distance. So maybe you put your ruler down here, and then what you need to think about is looking down from above to reduce any parallax error. And maybe the other thing you could do is you could put a marker up here potentially, and that holds the ball. So maybe you've got like a wooden block, or you've got some kind of special clamp stand, and basically you can have something that you bring the ball up to each time, and that means you know to the nearest millimetre where you're letting it go from. So we could use a distance sensor and data logger. Ben, yeah, perfect. I would say that a thing you could do, and again, we want to make A as big as possible. So we want to see how the amplitude changes with the number of oscillations. Now we know the whole track is 1.1 meters long, which means that the distance from here up to the end is about 0.55 of a meter. And so you want to have A being as big as possible. So we might want to make A bigger than 0.45 of a metre, because you don't want to be starting at 5 centimetres and just having it going back and forwards. You want it to be using the getting the maximum range of results as possible. You might video it from above, and if you video from above, you can then play back frame by frame, and that allows you to see the measurement. Because if you've got a meter ruler on the table, you're filming from above, maybe in the right kind of place. That means you can kind of freeze the frame when the ball stops again, as it basically rolls back and forward multiple times. So, Anch says it's difficult to measure from the centre of the circle or the ball, because it's very difficult to measure the middle. So you could measure from the side of the ball and measure the radius of the ball separately. Perfect. And again, this happens a lot. If you've got the ball, you're going to be measuring the diameter, and you want to measure that in at least 3 places. That then allows you to work out a mean, and you can divide that by 2 to get the radius, and you can add the radius or take it away from your measurement. So maybe the reading you get is 0.58 of a metre, but we know it's got a 2 centimetre diameter, so the actual reading would be 0.56, whatever. You could video it from the side. Menace to society, that's completely true as well. You don't have to do it from above. I think I'm just so used to having an above camera thing that I think I've just spent so long talking to cameras which are above that I just assume that's what everybody does. You don't necessarily need, you don't necessarily need a stopwatch as a reference, Horan, because this isn't about the time, it's about the number of oscillations. So the time is kind of irrelevant for this one. Okay, yeah. Right, the following set of results is obtained. We've got the number of oscillations, the value of A, and the value of the natural log of A. Complete the table by calculating and entering the missing values. If you get a question like this is easy marks. Okay, so this one here is just a case of can you put this into your calculator. So we've got our value of A in meters, that's important. So we're going to look at our natural log of that value in meters. So when it's, the natural log of 0.197 is minus 1.62. And then if we do the same, we want to have the natural log of 0.163, which is minus 1.81. Okay, so we've got some values there. On the next page, plot a suitable graph using this data and draw in a suitable line of best fit. So we've got a graph here. We've got the number of oscillations n at the top, and we've got the natural log of A, the amplitude in meters. And basically, then it's just a case of putting some numbers in. So, right, so I would say if we look at the numbers, we go from minus 0.9 to minus 1.8. So all of our numbers are going to be negative. And I'd say I'm going to go 0.80, and then we've got like minus 1.00, minus 1.20. And of course, this is just a skill that all of you have. You've developed it over many years of drawing stuff by hand. So there we go, we've got our thing there. If we put some numbers in, like when it's about 0, this is about minus 0.91, so it's like roughly here. This is just going to be like a super quick one. 1.1 is here when it's 2, 1.27, about here when it's 3, 1.45, 4 is 1.62, and then 5 is minus 1.81. So we've basically got some data like that. And then, of course, I would say in the exam, good night, Ibtisam. I know people having early nights or people in different parts of the world. I appreciate that. People are kind of getting ready for bed. Okay, so just going to kind of get something a bit like this so we can draw that in. I reckon that's a good line. It's a bit, the pencil's not the best, doesn't show up so well. So you can always, if you're happy with that, maybe go carefully over it with your pen in the exam. And of course, we've drawn the line of best fit. Explain whether the graph confirms the experimental nature of the change in amplitude in this particular case. So we've got basically a graph here that shows there is a relationship between the natural log of the amplitude and the number of oscillations. Why is a logarithmic scale used sometimes? Yeah, so basically for this, we know that here, the natural log of A is going to be related to the number of oscillations, I guess, and that means we can say that A is going to be proportional to e to the n. Okay, however, we've got to then kind of look carefully at what's going on, and I think a lot of this comes from the fact that basically paper 3 definitely kind of has quite a link to like doing kind of stuff with logs or natural logs, and if we said that A is equal to A naught e to the minus kn, okay, if we took the natural log of both sides, the natural log of A is equal to the natural log of A naught, the initial amplitude, minus kn, or the natural log of A is equal to minus kn plus the natural log of A naught. Okay, now effectively on the y-axis we plotted the natural log of A, and that's equal to the gradient, which is going to be minus k, and you can see here we have a negative gradient, so that means natural log of A is proportional to minus n, or e to the minus n, and that means on the x-axis we've got n, and then we've also got our plus c. So basically we've got a negative gradient, we've got maybe an intercept somewhere further up, but we don't know exactly where that is, but we know there must definitely be an intercept over here, because when this value is 0 we've got a plus c, and therefore A is proportional to e to the minus n plus e to the c. Is that right? That's probably not as good as it could be. Okay, so there, yeah, just ignore what I said then. Okay, that's not the clearest way to explain it. So basically what we have here is we have a relationship, an exponential change in amplitude in this case. Okay, that probably didn't make it that clear, that bit I just did there. So basically, because we can see that there's this straight line that's related to the gradient, which is going to be our decay constant, or kind of our damping factor in this case, and the y-intercept is going to equal the natural log of its initial amplitude. Okay, where has this equation popped up from? Oh yeah, so e to c is just a constant as well, isn't it? So yeah, that's right, isn't it? So natural log of A is proportional to n plus c, so I guess that's saying A is equal to e to the n times e to the c, or A is equal to e to the c times e to the kn. Is that right? And e to the c is just equal to the initial amplitude, which is why the y-intercept is equal to the natural log of A naught, and here the constant of proportionality is this kind of minus k. Okay, yeah, there we go. Where's the equation popped up from? It's basically we're saying, does the graph confirm the exponential nature of the change in amplitude in this case? So is there some relation to the amplitude, and how is the amplitude related to the number of oscillations? And is it an exponential thing? Well, the first clue we had is that you had to do something with a natural log. So if you got something with a natural log, then there's going to be some kind of y equals e to the minus x kind of graph. Okay, and basically if you plot a natural log value against another value and it's a straight line with a negative gradient, that means we do have this exponential decrease. Okay, should you be learning all the required practicals for paper 3A AQA, says Joel? Yes, I think you should. but you don't need to learn them from scratch. You just need to remember what you've already done. And don't forget that as you've been revising for paper 1 and paper 2, you will have been revising about electric fields, or how to like maybe use a search coil or something inside a Helmholtz coil to look at the magnetic field at different angles. You'll have been learning about diffraction gratings or double slits. So a lot of it is stuff you've already learned the theory of, and I think you do need to be aware of all the practicals you've done, how you've dealt with uncertainties, and how the equipment's been set up. Yeah. Any prediction on the practicals coming in section A? No chance at all. Nothing to predict. I do have a video coming out tomorrow. Actually, what I can do, because all of you lot are there watching, I recorded a video this morning. I'll just find the link to it now, and I've put it into a playlist on YouTube. I haven't really, but it's still unlisted. So if anybody wants to see my video about paper 3, I'll make it live tomorrow. I'd say that if you click on the link that I've just put up in the chat, you can watch the video before other people do, and that'll be out tomorrow at some point. I'll maybe randomly put it out maybe in the morning. Yeah, I reckon somebody says they beg AQA just to give a normal paper. I reckon it's going to be all right. Okay, but this is an exclusive thing. Hopefully you can all see that. Yeah, material stuff, there wasn't much of that on paper 1 and 2. Potentially there could be something about the Young modulus found in different ways. But again, they always have their unique twist. So it's not just a 6 marker of saying, how do you work out the Young modulus of copper? There's going to be a bit more to it than that to kind of differentiate the kind of learning. So yeah. Yeah, I reckon there's nothing more I can do really to help you out tonight. So I hope all of you have a good evening. Uncertainty will definitely come up. Am I going to do another live stream tomorrow? Ansh, yes. If you look at alevelphysicsonline.com/live, you can see links to all of the live streams I've done in the evenings. There's about 30 of them now. You could probably watch me continuously for the next 24 hours if you wanted to. I could just be that voice that's just kind of speaking in the background while you're revising. And basically, yeah, I've got loads of videos out there. So yeah, what's the best way to revise this? Menace to Society. The best way to revise is to go to my Physics Online shop, which is physicsonline.shop, and buy a set of papers. I'm just going to see if anybody's actually bought any this evening during the stream. So yeah, let's have a look. Have people? Oh yeah. So we've got. I'll do a shout out to Ewan. A shout out to Emma. Thank you so much for buying a pack, and also Anderson. You've bought stuff during the stream, which is amazing. So thank you for doing that. Oh, actually, we've also had orders from Hannah and. Sorry, let me just see who else we've got. Hannah and a few other people. So yeah. Right. That's good. People are buying stuff. Thank you so much. And also your support allows me to be, doing more stuff for you in the future. It is a shameless plug. However, I've just done a completely free live stream for an hour. So I'm going to try and plug the stuff that I'm selling, because I do genuinely think that having this in front of you will just help you prepare that little bit more, for the exams coming up. Does it come with answers? Of course it does. And also, if you actually get the thing, it also comes not only with answers, but it comes with work solutions. So you get like your normal kind of answer sheet like you would for an exam board, but there's also work solutions for everything that I've done there for you to kind of help explain things. So that all comes with it as well. Thank you very much. Good night, everybody. Eva, Jude, Menace to Society, Ibtisam. Yeah, good stuff. Ben, everybody else, thank you so much. Meme Lord, Ibtisam again. It's great to have all of you. What's the biggest fish I've ever caught? Haven't really ever been fishing. I think I shot a bird when I was a teenager with an air gun. First shot, direct kill, and then I felt incredibly guilty. So I did shoot a little bird out of a tree. That wasn't a good thing. But I haven't actually been fishing, I don't think. Have I ever caught a fish? I've been on a boat where we've caught like some fish about that big, but they stink. I don't really like the smell of fish so much. Yeah, that's about it. Right, anyway, got other stories about Afghanistan. That was a different kind of hunting. Anyway, good night, everybody. I'll see all of you again soon. Bye.